Okay, so we saw in the last video that the integral of 1 over x squared, right? The integral from 1 to infinity, it's supposed to be infinity, of 1 over x squared is actually equal to 1. That this is an improper integral. The right-hand endpoint actually goes off to infinity, really meaning that there's no, if you think in terms of area, the area just goes on forever. But somehow we get a finite area. And so in this case, finite area. In this case, we say that the improper integral converges. We say that, yeah, we use this terminology, converge. So let me write that down. Converges. So that's the term. Okay, so anytime we get a finite, an improper integral, which is an integral that we sort of don't know until we examine it, whether it's finite or not. Once we discover that it is finite, we say it converges. Let me give you kind of another example. Something kind of dumb. What about something like the following? What about the integral from 1 to infinity of x dx? Right, we know, okay, so by definition, that's the limit as the right-hand endpoint goes to infinity, the integral from 1 to b of x dx, which is the limit. Remember to keep writing your limit, but this is 1/2 x squared from 1 to b. And you can see what's going to happen here. It's 1/2 b squared minus, I guess you plug in 1 and you just get 1/2. But it doesn't really matter that 1/2. You're getting this b squared and you're making b larger and larger, right? B is getting larger and larger, which means b squared is getting larger and larger. So this blows up to infinity. So I'll just say equals plus infinity, because clearly, right? And so we say this improper integral, in this case, we say it diverges. So if we can't get a nice, honest value out of it, we use the word diverge. So that's the terminology. If you look at the picture of the graphs in these two cases, you know, the graph of x, let me draw some axes here. The graph of x is, I mean, it's silly, right? It's just like this. By the way, there's no reason to start at 1 here. It didn't really matter, but you can see, right? If I start at 1, and just start making the area under the graph, it's kind of ridiculous. Like, it's clearly getting bigger and bigger and bigger as you slide b to the right, right? You make this b and you slide it b and you slide it to the right, and the area is just going to get bigger and bigger. So this had no hope of converging. This is obviously going to diverge as b goes to this, you know, as b slides to the right. I almost think about fixing the left-hand endpoint and then sliding, having a little slider here that's b, and then you can slide it back and forth, and then we're just really trying to see what happens as we slide it further and further, and it's clear. In the other example with 1 over x squared, well, what's going to happen? I mean, let's just think about this. I hate when it doesn't give me the straight line automatically. Notability, don't be finicky. There you go. We saw the graph of 1 over x squared looked more like this, right? And so here, it's because of the horizontal asymptote, right? It's the fact that this was going toward, that the function itself is going towards 0, right? It's sort of necessary. I guess what I'm going to say is that it's necessary in order to have a chance to converge. Any chance to converge. So meaning that this is actually a finite area. Like here, just look at the two differences. This is getting bigger and bigger. This is getting the graph's going up. And so this is getting bigger and bigger, this area. Here, the graph is approaching the x-axis. And so it gives us a chance to somehow cut off a finite area. So in order to have a chance to converge, we really need the function to go to 0 as x goes to infinity, right? Otherwise, I mean, I can even do something like, I mean, you can do things that look almost the same. Like, for example, what if I did f of x is like 1 over 100 plus 1 over x squared, right? All that would do would move this graph up a fraction. But think about what happens when you integrate this, right? If you integrate from 1 to b, well, the 1 over 100, we're anti-differentiating this function. So the 1 over 100 becomes 1 over 100x. And we saw this becomes minus 1 over x. So this would be 1 over 100 times x minus 1 over x from 1 to b. And even though there's a 1 over 100 here, you're sticking a b in here, which is going to get bigger and bigger and bigger. So that's 1 over 100 times b minus 1 over b. And this expression right here will go to infinity as b goes to infinity. And you can sort of think about it, right? If we drew this, let me sort of draw out schematically. I'm not going to try to make notability draw straight lines. Actually, I really kind of need that here. Come on, notability. Be nice to me. There we go. If we think about this function up here and we want to plot it, then, and I kind of zoom in, at least vertically, there's this 1 over 100 here. And there's kind of this barrier. Notability be nice. So there's this barrier right here. And if we draw the graph of 1 over 100 plus 1 over x squared, it's going to look like this. And it's never going to actually, it's going to get closer and closer to this dotted line whenever we touch it. And then if we want to think about the area underneath, right, we kind of have, you know, the area from 1 to infinity. We have this area we looked at before, which is finite, but now we have this area right here, which is definitely not finite because it's a rectangle that's just going to keep growing and growing, right? Again, as we slide the b to the right, this is going to go to, this area is going to go to infinity. And so that's kind of, you can see why. I'm trying to give a justification for this right here, that you really need the function to go to 0. That's the only case you're going to ever be able to have a finite area. Okay. But the next question is that enough to guarantee it? So, and I claim no. I claim the answer is no. So, but f of x going to 0 is not good enough. remember we were so surprised that we got a finite area. So not good enough to do what? To guarantee convergence. Like, I still think we were surprised in the last video that we got a finite area. So let me just give you a different example. So let's think about something else that also, instead of having x squared on the bottom, I'm going to put the square root of x on the bottom. So in fact, the graph is not that much different looking. As x gets large, the bottom eventually will get large, and so this will go to 0. And also if you plug in x equals 1, you do get just 1. So I mean, it's something that doesn't look that different. I'll show you the two graphs in a moment, but let's just analyze this. So this equals, by definition, the limit as b goes to infinity of the integral from 1 to b. I guess this is x to the minus 1/2 power dx. And so that is, I'm just going to keep writing my limits here. Maybe I should have just done the integral first and then put the limits in later. So the antiderivative of x to the minus 1/2 is 2x to the 1/2, right? So that's still the limit. But now that's 2 root x, and we're plugging in b and we're plugging in 1. So that's 2 root b minus 2 times root 1, which is just 1. So we get this expression now. And now look what happens as b gets large. When b is 100, well, when b is 1,000,000, let's say, when b is 10 to the 6th, then 2 root b minus 2 is 2 times 1,000. Square root of 1,000,000 is 1,000. So that's 2,000 minus 2, 1998. If b is 10 to the 20th, then you get, then this thing is 2 times 10 to the 10th minus 2. Still big. This goes to infinity. So this integral diverges. So even though 1 over root x behaves kind of like 1 over x squared, one is finite, one is infinite. So let me just recap that. The integral of 1 over x squared, this one converges, but the integral from 1 to infinity 1 over root x dx diverges. Okay, and actually, if you look at the graphs of these two functions, you might start to get a sense. Let me show you. So, okay, hopefully you see this here. The blue graph is the graph of 1 over x squared. The red graph is the graph of 1 over x. If you zoom way out, they kind of look like the same shape, right? But as you zoom in, see what happens. They both go through 1, and when x equals 1, you know, they both of these functions equal 1. But the blue graph, because you're squaring the denominator, you're making the denominator bigger faster. It sort of dives down towards the x-axis. So the asymptotic behavior is the same. They both go to 0, but you're diving down and you're choking off less area. Whereas under the red function, there's just a lot more area as you go, right? And you can even sort of like say, well, oh, but over here they look like they're the same. You know, they're both just against the axis. But if you zoom in, it's kind of fun to play with this. That's why I really like the Google search bar as a plotter. Notice, see lots of area under the red, but the blue is hugging much tighter. The blue looks like it's on the axis. Turns out it's not. If we zoom in enough, we'll start to see some space, right? So we're zooming in enough and we're seeing some space there. But so there is area, but it's choking off much less, and so much less area. So somehow that's enough for it to be, for the area to be finite, the area under 1 over x squared to be finite. Yeah, if I just zoom out again, you kind of see. Well, I guess if I zoom out enough, I just get these. It's really hard to see what's going on there. But again, it's like you can just see what happens here. So it turns out that at some point, right, like this, if it dives down, if the graph dives down to 0 quickly enough, dives down towards the x-axis quickly enough, you can get a finite amount of area under it. If it doesn't, again, with the red graph, you cannot get a finite amount of area. We saw that this actually gets bigger and bigger, the area under the red graph. And that's what's going on in the, let me go back to the, this might take a minute. See if I can do this. If I can get back to the, oh, now it's gonna act weird until, give me a second, sorry. It's always a technology. Okay, that's just basically what I'm trying to describe here, is that this one dives down to the x-axis, this function, so the integral actually converges, the integral is actually finite. This one makes its way down to the x-axis more slowly, which lets there be enough area. And in fact, sort of the avatar for convergence versus divergence is these 1 over x to a power functions. For is the function 1 over x to the p power for different values of p. Because they all go to 0, I guess different values of p, we really want p to be positive because we want there to be an x in the denominator. Because the limit, 1 over x to the p goes to 0 as x goes to infinity. But like when p equals 2, the integral converges. When p equals 1/2, the integral diverges. And then you get this big question as like, where's the tipping point? Like, if I change this power, like what happens to 1 over x to the first? And that's actually what we'll analyze more carefully in the next video. But it seems kind of random to focus so much on functions that look like this, except they have the property that the height 0 is a horizontal asymptote. So the function goes to 0 as x goes to infinity. That ends up being very important. So that's why if you look in textbooks, and the next video I'll do, that's why we focus on these kind of functions. Okay, I will stop there.